two small objects, masses 0.03 kilograms and 0.06 kilograms, and each have a charge of -4 nanocoulombs. That's -4 times 10 to the -9th power. They're held together by a 0.02 meter long length of insulating string, and no charge can flow through the string. The objects are initially at rest on a horizontal, non-conducting, frictionless surface. So the first thing we want to do is calculate the ratio of Fe, the electrostatic force, to Fg, the universal gravitational force between the two objects. So we can write them as K Q1 Q2 over R squared divided by G M1 M2 over R squared. And you could calculate each of these forces individually and then just divide them, or to make matters a little bit easier, since both have an R squared, since the numerator and denominator both have an R squared in the denominator, we can just cancel them out. So this just simplifies to K Q1 Q2 over G M1 M2. And then just plug in the values. K is 9 times 10 to the 9th. The G was 6.67 times 10 to the -11. Both Q's are 4 times 10 to the -9th. Remember, you don't have to include the negative sign on the actual charge itself. That -4, just make it a +4 for both charges. And the M1 is 0.03, the M2 is 0.06, and for that you should get an answer in scientific notation of about 1.2 times 10 to the 6th power, which basically what that's saying is that the electrostatic force between the charges is over 1,000,000 times bigger than that gravitational force between the charges. So you wouldn't even really notice that gravitational force, which is why if you were to draw a free body diagram for one of these charges, you wouldn't even include that universal gravitational force on there. Part B, by what factor would the ratio in Part A change if the connecting string were half as long? Well, the R's, which are the distance between them, those R squareds canceled out, so it doesn't matter what the length of the string is. It's not going to change the overall ratio. It's basically what happens is, since they both have an inverse square relationship, if you decreased that distance by a factor of 1/2, then 1/2 squared is 1/4, but that 1/4 in the denominator puts a 4 up in the numerator. So the electrostatic force is 4 times as much, but the gravitational force is also 4 times as much. So since they both go up by the same amount, then it doesn't really change anything. So that's why the factor in Part B is just 1. Part C, calculate the tension in the string. So this is just a simple application of Newton's first law. Since neither of these masses are moving, you can just draw a free body diagram on just one of these masses. So let's do a free body diagram on, let's do it on M1. So we can just say there's the force of tension in the string, which is counteracted by the electrostatic force pushing them apart, the Fe. And remember, we're not going to include the gravitational force, that universal gravitational force on here, because it's negligible. So, and then if it's on like a table, there's going to be a gravitational force and a normal force on it as well, but those don't really matter right now because all we're concerned with is calculating the tension, which perfectly balances out with the electrostatic force. So, just use this formula, but this time with the R squared, since we're just using the electrostatic force, and that's going to be the same as the tension force. So you'll get a pretty small answer. It's going to be in scientific notation, it comes out to 3.6 times 10 to the -4th newtons. In Part D, the string is now cut, so calculate the magnitude of the initial acceleration of each object. So now this is a Newton's second law problem. For Newton's second law, the acceleration is equal to the net force on the object divided by the mass. We're trying to find it for both objects, so we get A1 for mass M1, and we'll find A2 for the other mass, M2. So in both cases, we would need to know what the net force is. Well, the only force acting on it after the string is cut is going to be that electrostatic force, because the string's cut, the tension is no longer there now. So we could put in the Fe for that net force, but in the previous step, we just showed that Fe was equal to Ft right at the initial point. So we could just put in the Ft, the value for Ft that we got in part C, since we know it's the same as Fe at when the string is first cut. So if you put in the 3.6 times 10 to the negative 4 divided by m1, it's going to give you a value of about 0.012 meters per second squared. And if you divide that same force by m2, that was the 0.06 kilogram mass, you get an answer of 0.006 meters per second squared. In part E, we're drawing a graph of acceleration versus distance, and from Newton's second law, you know that acceleration is directly proportional to the force. So it might be easier for you to think of this as being a graph of force versus distance, and in that case, we would just use this equation right here, the electrostatic equation, because as the distance between the two charges increases, as this r increases, which is we're using as the d on this graph now, but as that distance increases, the Fe will decrease. So we know the initial value of the distance because it's the distance between the two charges. So on the graph, we can label the 0.02 meters, and we also know the initial value of the acceleration, and this is for mass 2. So the initial value, right when the string was cut, we calculated was 0.006. And that would be in meters per second squared. I'll just put the units actually on the graph. And that distance was in meters. So that's going to be your starting point right there. And then as the distance increases, it's an inverse square relationship with the force. So that's a graph that kind of looks like this. It's concave up, and it approaches the axis, but never quite it goes to zero. It's asymptotic with that horizontal axis. And in part F, describe qualitatively, so that means without any numbers, what happens to the speeds of the objects as the time increases, assuming that the objects remain on the horizontal, non-conducting, frictionless surface. So because you have an acceleration, that means as soon as it's cut, they're going to start increasing in speed, but that increase in speed, because the acceleration is getting less, it's still increasing in speed because it still has a positive acceleration, but it gets to the point where that increase in speed almost goes away, because now here the acceleration is almost becoming zero, which means that the increase in speed is becoming zero. We're not saying the speed's becoming zero, we're saying the increase in speed is becoming zero. So they kind of get to the point where they reach like a fixed speed because there's no more force acting on them. It's like a Newton's first law thing, that once they've reached that certain speed, once they're kind of far enough away from each other where they barely feel that electrostatic force, they're still moving, they just have a constant speed because the acceleration is zero.